Welcome back. In the previous video, we looked at a couple of iterative methods. We've seen Jacobi iteration, Gauss-Seidel iteration, SOR, and we have seen that they are all of the type that you see on the current slide. So we split our matrix A as m minus n, where m is, for instance, the diagonal. And then we rewrite the linear system and we come up with an iterative method that looks like this, and that's a fixed point method. So that's what we have already seen. Now I'm going to ask a couple of questions because I've presented the methods but didn't concern myself at all whether this is going to work, whether it converges, and if it converges, how fast or how slow, and so on. So let's see. The questions I'm going to be looking at in the next couple of minutes are, say that this works. So say that our xk vectors converge to x star for k tending to infinity. Is x star, so the limit of my vectors, is it a solution of the linear system? The second question, does this work? Will it converge? Under what conditions will this work? And then finally, if it converges, how many iteration steps do I need to take? How fast does it go? How many steps? How fast does the error go down? Stuff like that. So let's see. First question is easy, because if xk converges to x star, as we have here, then if we plug it into the equation up here, we know that both xk plus 1 here on the left, this one here, goes to x star, and also xk goes to x star because they have to converge to the same limit, x star. And then if you plug that in, we find this equation here for x star, multiply with m, and then move the n term back to the left side, and we see that indeed we have a solution of the linear system. So that's great. So first question is answered. Yes, that's correct. It happens. Next question. The next question is, does it converge? And for that I need a lemma. So the lemma we have here on top, if you have a square matrix G, so G is going to be m inverse n from the previous slide, the iteration matrix of our current iteration, then we have already seen this property. G to the power k will go to the all zero matrix if the spectral radius, in absolute value the largest eigenvalue, is less than 1. So if you think about numbers, it always helps to look at very small examples. So if you have a number that's a 1 by 1 matrix, then it says that powers of that number will go to 0 if the number, well, the spectral radius for a 1 by 1 matrix, that's going to be the absolute value of that number if it is less than 1. So if you have a number in between -1 and +1 and you take powers, it goes to 0. So that makes sense. Now, the next theorem is going to use this. And it tells you that the fixed point method with this G matrix here is going to converge for any initial vector. So it doesn't matter what we choose as an initial vector. We can take any starting vector. It will work if the spectral radius of the iteration matrix is less than 1. So that is going to be the criterion. So let's try to prove that. And I'm going to prove that writing here, what I would normally do on the blackboard, I'm going to do on my iPad screen now. So let's move to the screen. Let's take a piece of paper here, so an empty piece of paper, and let's try to prove that. So what do we have? Well, what I would like to show is that the iteration xk plus 1 equals gxk plus f converges for any starting vector x0 in Rn is equivalent to spectral radius of G is less than 1. So what I'm going to prove is not both sides of the equation, but the interesting bit, what I consider the interesting bit. So I am going to assume that the spectral radius is less than 1, and then I will show convergence. So if we have this, we know that the matrix identity minus G is non-singular. Because we've seen this argument already a couple of times. If lambda is an eigenvalue of G, then 1 minus lambda is an eigenvalue of identity minus G. Now, all the eigenvalues of G are in absolute value less than 1. So that means that 1 minus lambda can never be 0. So 0 is not an eigenvalue of identity minus G. So identity minus G is non-singular. So what that means is the equation x is gx plus f, or identity minus g times x equals f, has a unique solution. So I'm going to call that x star, because this is going to be the limit, right? So x star is identity minus g inverse f is the unique solution of the equation. And then what I'm going to do is, on the one hand, I'm going to consider the iteration. So the iteration says that x k plus 1 equals g x k plus f. On the other hand, we have that x star equals gx star plus f. And now I'm going to subtract them. And if I do that, let me get a little bit more paper. Then we have that x k plus 1 minus x star equals g x k minus x star. And the interesting thing is that you see that the f vector, so here the vector f on the right hand side and the vector that's also in our iteration here, that drops out of the equation. So apparently the f here, even though we add it in every single iteration step, it does not influence the convergence of the method. And basically we're here now, because what we currently see is that, well, xk plus 1 minus x star, so that's something like the distance between the approximation in step k plus 1 and what we're looking for, because x star is what we're looking for, is, so let me write that down. So this is something like the, let's call it the error in step k plus 1 is the G matrix times, and this is precisely the error in step k. So of course you can repeat this. So I'm going to copy this, copy to a new page, and let's paste it here. Okay, so if you repeat this one more time, then you see that x k plus 1 minus x star is g squared x k minus 1 minus x star. And you can go all the way back to the initial error, and then you get here g to the power k plus 1, and then we have x 0 minus x star. Now, with the lemma that we have seen on the slide, what we see is that g to the power k plus 1 converges to the all 0 matrix for k tending to infinity. So the conclusion is that x k plus 1 minus x star converges to the 0 vector for k tending to infinity. So the conclusion is that indeed these xk vectors converge to the solution of the linear system. Now let me switch back to the slides. And here, let me also switch on myself again. You can see my face again. So what we see here is that we have convergence if the spectral radius is less than 1, but the spectral radius can be hard to compute for the iteration matrix. But we've already seen that if you take an induced matrix norm, the 1 norm, the 2 norm, the infinity norm, that it's an upper bound for the spectral radius. So if you have such an iteration matrix G, you compute an induced matrix norm, for instance the 2 norm, and you see that it's less than 1, then you know that you will have convergence for your iterative method. And once more, the f in the iteration, so this f factor here is not important. The initial guess is not important for convergence. The only important property is the spectral radius of the G matrix. Now, what we have also seen, or we haven't really seen that, but we'll come to that in a second, is if the spectral radius is much smaller than 1, we have fast convergence, so we need few iteration steps. If it is less than 1 but close to 1, 0.9, 0.99, something like that, we have very slow convergence and we'll be needing many iteration steps. Now, this is more or less for reference on the next slide. It's not terribly important. But what I want to make you familiar with is that we can express this iteration that we have seen already a couple of times here. We have formulated in terms of the x vectors, which makes sense because the x case is what we will normally compute in a script. But you can write it in different ways. So first of all, as a little ingredient, the G, the iteration matrix, is M inverse times N. And if you say that N is M minus A, and you plug that in, we have here a different expression for the iteration matrix. Okay. Now, the error is defined here as x star, so the true solution of the linear system and our current approximation, xk. If you define this to be ek, then you can easily see that for the error, that's basically in the proof that I just wrote on the slide, for the error we have ek plus 1 is g times ek. So instead of looking at the x factors, you could also formulate the iteration for analysis purposes, also in terms of the global error. We can also look at the residual. So we've already encountered the residual a couple of times in applications, and the residual is b minus ax. It's normally denoted with r for residual. You can easily see that if you apply a to the global error, if you apply a to the global error, that is ax star minus ax k, and this is precisely b minus ax k, and this is what we have just defined to be rk. So apparently this relation holds between the residual and the global error. The A matrix is in between there. Okay. You can show that the iteration can also be formulated in terms of the R matrix here. Now, what you can finally do is write the iteration in this way here, M inverse times RK. This does not make a lot of sense now to do it like this, but later on when we will study Krylov methods, well, I say we will study them. If you choose to attend the master's course in scientific computing, you will study them. And there you have a similar expression. Let me wipe this blue stuff here. So, like this. Then we have a similar expression, but instead of M inverse, there is an H matrix there. This is just for later. Here is a little overview. So we can write the iteration in terms of the X. That's what we have basically been doing all the time up till now. You can look at the global errors. You can also look at the residual. And finally, you can also look at the what is called the update form. So we have xk plus 1 as an update to xk. Now, a little bit more on the norm of the iteration matrix. So what I'm going to do here is I'm going to assume that the spectral radius is less than 1, because then we have convergence. We denote the fixed point by x star, and the length, the norm of the difference of x star and xk, so that's ek from the previous slide, I call this number, so the number ek. So that's the distance of the current approximation to the fixed point in whatever length you would like to use. So here is a theorem that tells you a little bit about the link between speed of convergence, because you would like ek to go to 0, and the spectral radius. Apparently, every step of the iteration you take, the distance is going to be multiplied with the spectral radius. And here you also see why it needs to be less than 1, because then we actually have convergence. So it says here proof. So I am going to write again, and I need a little bit of white space to do so. Let me switch to this screen only, and let's try to prove why this holds. Now, what I need to show is that ek is spectral radius of g ek minus 1, and actually it's said is approximately, so it doesn't hold exactly, but it's approximately true. And to prove this, I am going to make an assumption that makes the proof more convenient. So it is not necessary, but it makes the proof a lot easier to understand if we assume that G has n independent eigenvectors. So G is n times n, so basically we say there is a basis of eigenvectors. So let's call these V1, V2 up to Vn, the corresponding eigenvalues. I call lambda 1, lambda 2 up to lambda n. And of course I can label these myself. So what I'm going to assume, I'm going to label them in such a way, label such that, well, basically that lambda 1 is the biggest one. So lambda n is going to be smallest, and it's going to be less or equal lambda n minus 1. And then I can go all the way up to lambda 3, which is less or equal lambda 2, which is strictly smaller than lambda 1. So this is like we have seen in the power method. I'm going to do something similar to what we have seen in the convergence of the power method. And this needs to be less than 1, because we assumed that the spectral radius is less than 1. Lambda 1 absolute value is now the spectral radius, so it needs to be less than 1. So let's write that down. Then spectral radius of G is lambda 1, absolute value is less than 1. Now we are going to start our iteration with x0. So the initial guess for our iterative method, initial guess x0, and the initial error, so how far this is away from the solution of the linear system, is x0 minus x star. Now, since the v's are linearly independent, they form a basis. So I'm going to write this vector here as a linear combination of the eigenvectors. So we can do that for some coefficients beta j. It's not very interesting what values these beta j's are, just that I can write it like this. So for some beta j, and these are coefficients, so these are real numbers. Now we are going to do the iteration with g. G is the iteration matrix. So if you have g to the power k applied to this vector, so basically we've done k iteration steps, then I can plug in the sum up here, and if I do that and use that we are dealing with the eigenvectors here, I can write this as beta j lambda j to the power k v j. And now I'm going to use an argument as we have seen in the power method a couple of times. So I'm going to write this as the first one, beta 1 lambda 1 to the power k v1 plus the rest. And the rest is the sum j equals 2 up to n beta j lambda j to the power k vj. And now I'm going to say, well, this is approximately only the first term. Since lambda 1 is really bigger than the rest, I'm going to say that, and let's put it on the next slide, I'm going to say that g to the power k x0 minus x star is approximately equal, and then I just take this first term, beta 1 lambda 1 to the power k v1, and I forget about the other terms. Now I needed to say something about ek, which was defined as the norm of x k minus x star, which is the norm of g to the power k x0 minus x star. And well, apparently we have just found that this is approximately the norm of beta 1 lambda 1 to the power k v1. Then we go back all the way to the start of this course, and we know that we can pull out the scalars, and this is absolute value beta 1 times absolute value lambda 1 to the power k times norm v1. So the conclusion is Conclusion. EK is approximately lambda 1 times EK minus 1, because we have a similar expression for EK minus 1. And this is precisely a spectral radius of G times EK minus 1. And that is what we needed to show. So this concludes the proof. And now let's go back to the slides. So here is basically what we have just found. And let me get myself back into the video. So what we have found is that EK is approximately the spectral radius to the power k times the initial error E0. Now if you take logarithms on both sides, you see that the logarithm of EK is approximately, and then we can put the exponent in front of the logarithm k times the ln plus the ln of the initial error. And if you would now make a plot where you put ln EK on the vertical axis and you plot it as a function of k, you would get a straight line, because the equation we have here, this equation in the box, is a straight line where this here, the ln of the spectral radius, is a slope, and this here is the y-intercept. And so what you get is a straight line, and ln of rho g is the slope. Now, of course, the line is going down, so the slope is negative. So minus this number is defined as the convergence rate, and the spectral radius itself is defined as the convergence factor. Now, to wrap up this bit on convergence, what I would like to do is look at convergence results for special matrices. So are there any matrices for which we can immediately tell that Jacobi, for instance, is going to converge? Well, we can do that. So the property that is important here is diagonal dominance. So in the blue box on the left, you see diagonal dominance. A matrix called strictly diagonal dominant if the diagonal entry, absolute value, is bigger than the sum of the off-diagonal entries in the same row, also absolute value. And we say weakly diagonally dominant, and this is in between parentheses, so A is also called simply diagonally dominant. If we don't say strictly or weakly, it is diagonal dominance, and that is if you have a bigger equal sign here. So it can also be equal. So if you recall, we've already encountered a couple of times this matrix with 2, minus 1, minus 1, 2, minus 1, minus 1, 2, minus 1, and so on. So what you see is that this matrix for each, well, for row 2, 3, and so on, you see that the diagonal entry is 2 and the sum of the absolute value of the off-diagonal entry is also 2. So there we have the equal sign here. And here in the first row, you see that the diagonal entry is really bigger. So this matrix, that we will meet again a couple of times, that is diagonally dominant or weakly diagonally dominant. Now, we also looked at irreducible before. Basically, a matrix is irreducible if you cannot split it into something like, let's write B, C, D, 0. So if you can write a matrix like this, basically part of the unknowns are uncoupled from the rest. If you would solve a linear system, you could solve a linear system with these guys first, and then find these guys, the unknowns corresponding to the B matrix, later. This is called reducible if you cannot do that. So if all the variables are connected together, like for instance here, all the unknowns are connected together, then a matrix is irreducible. And a matrix is called irreducibly diagonally dominant if it is irreducible, diagonally dominant, and if you have inequality, strict inequality in at least one row. So this matrix here is a matrix that is irreducibly diagonally dominant. Now, For Jacobi, you can show that if your matrix is strictly diagonally dominant, then it will converge. And the proof is not so difficult, and we're going to do that. So let's grab some paper, I would say, white space. And let's go to iPad only. So what we have here, so what the theorem says is that if A is strictly diagonally dominant, so that means that the diagonal entry A, I is truly bigger than the sum of the rest, sum over j unequal I, A, ij. And that should hold for every row for strictly diagonally dominant. Then Jacobi converges. So the proof is, well, what we need to show is that the row of G, and that is the row of D inverse E plus F, because that is the iteration matrix that belongs to Jacobi iteration, is less than 1. Now, as I already said, the spectral radius is hard, but the infinity norm is quite easy here. So what we're going to do is we're going to we're going to estimate the infinity norm of the G matrix. So what is the infinity norm? Well, we already have seen a characterization for that. It's the maximum over I, the sum over J, Gij. Now, if you look at the expression I have for G here, then it is clear that this is maximum over I. And then D inverse, so the G matrix is D inverse E plus F. So D inverse, that gives rise to 1 over the diagonal entry. And then we get the sum over J unequal I, that's the E plus F part in the expression, Aij. Now what is interesting is if you look here what I wrote at the very top of this slide, so here we see that this Aii is really bigger. So that means that this number is less than 1. So the conclusion is the spectral radius of our G matrix now is less or equal, that's a general property of the infinity norm, which is less than 1. So the conclusion is that indeed for Jacobi we have convergence. So that concludes the proof. Now let's go back to the slides. So here we have the slides again. And you can prove more generally, as it says here, that Jacobi and Gauss-Seidel, both of them, if the matrix is strictly diagonally dominant or irreducibly diagonally dominant, then they will converge. So I'm not going to prove that, but you can show that. So it's a bit more general than the theorem that we just proved. Now finally, they went into a bunch. We had Jacobi, we had Gauss-Seidel, and there was also SOR. So for SOR, I'm also going to present some results. I'm not going to prove them. So if you have a matrix that is symmetric positive definite, which is very, very nice, that's very nice property for a matrix to have, and if the diagonal entries are bigger than 0, then the SOR matrix, the SOR method, will converge for any relaxation parameter omega, as long as you pick it in between 0 and 2. Now remember, omega equals 1 is Gauss-Seidel, omega less than 1 is under relaxation, slower convergence in general, and omega bigger than 1 will speed up convergence. So apparently we should pick it in between 1 and 2. Now, the idea for the whole method is to speed up convergence, and we will come to a numerical example in a second that this actually will work. There is a theoretical optimal choice. So if you choose it like this, so a horrible formula where the spectral radius of the Jacobi matrix is in there, so usually you don't know that. But what you see then is that you get much faster convergence. So here we have the spectral radius of the SOR iteration matrix as a function of omega. And you see in this picture that there is a point where it is very small compared to the rest of the region. So let's look how this works. I mean, this SOR is a lot more complicated than the other methods we have seen, so it should pay off somewhere. So what I'm going to do is I'm going to look at the boundary value problem that we have seen before. So we have the second derivative of u, apparently minus u double equals 1. And if you discretize that with central differences, you get our famous matrix with 2's and minus 1's that we've seen a couple of times already. Because the right-hand side is 1 here, we get h squared here from the central differences. If you write it out, you will see that. I wrote a little MATLAB script. And what you already see here in this MATLAB script is that I store it. You don't have to know this command, but this tells MATLAB to build a sparse matrix, so take into account that we have many zeros, and I'm going to specify it by means of its 3 diagonals, the -1, 2, and -1 diagonals. So E is a vector with only 1's on them. Now, for this problem, I also know the exact solution. I can solve this boundary value problem. Since I took a very simple right-hand side, I know that the solution here is 1/2 times x times 1 minus x. That's the solution of this boundary value problem. The ordinary differential equation with boundary values. And here I have implemented Jacobi iteration. And of course you can easily change this one line that does Jacobi to do Gauss-Seidel, SOR, and so on. So I've run the experiment for a... let's see, I took the number of grid points to be 50, which means that our matrix is going to be 50 by 50. And what you see is here on the horizontal axis is the number of iterations. On the vertical axis, on a logarithmic scale, we have the error. So here we know the exact solution, so we do... we find the solution of the linear system, we compare it to the x case during the iteration. You see the slowest method here, this is Jacobi. So Jacobi is like the simplest method, and it's also slowest. Gauss-Seidel, if you look here, this is Gauss-Seidel. It is approximately twice as fast. So if you look at the slope of the straight line, we get straight lines here. The slope of the red line is half of the blue line. And then finally, we have SOR. So SOR with an omega in between 1 and 2. And that's the yellow one. And you see that's already faster than Jacobi and Gauss-Seidel. And if you make the optimal choice, apparently you can compute that here, you get the purple one. And you see that it goes very fast to 10 to the power minus 15, which is the machine accuracy of MATLAB. So as soon as you're there, it's the best that you can hope for. You always make small rounding errors of this size. So you see that you get very fast convergence towards the solution of the linear system. So this concludes the bit on the convergence of these basic iterative methods. And what I will do in the next video is give a bit of an outline of modern projection methods. So they are the faster iterative methods, but they are also a lot more complicated than the methods that we have studied in this video. So thank you, and I'll see you in the next video.